In this lecture, we're going to start looking at chemical properties of, excuse me, of alkanes. That is what reactions they undergo. So getting into it right away, what I want to first start off by telling us is that when we learn about new reactions, we're typically focused on being able to accomplish two things related to that reaction. So with any new reaction, we want to be able to there's kind of two principal things that we want to be able to do. And that is, number one, predict the products of the reaction. And really, there could be an off-target goal of this, and that is to propose how to make some target using the new reaction. And that target's going to be a molecule. Additionally, so let me just rephrase this. So we have this new reaction. We just learned how to use it. Now, what does it mean to use it? It means to sort of take that reaction and apply it using some number of molecules, various molecules. If you can imagine reactions of alkanes, maybe we have methane, ethane, propane, whatever, as our starting materials, and we do the reaction on those starting materials. Let's try to predict the outcome. Now, similarly, we want to be able to look at products and predict how we could have made that product, that target molecule, using this new reaction. The second thing we want to be able to do is very strongly related to number one, or is very useful for helping with number one, and that is we want to be able to propose a mechanism for how the reaction occurred. And this really uses curly arrows to explain what happened. So this is our curly arrow notation that we learned about in the last module. To describe what just happened. Okay, so with any new reaction, we're going to be talking about many reactions now, going into the chemical properties of alkanes and then haloalkanes, so on and so forth. For the rest of the semester, we're going to be talking about reactions because they lead to the transformation of matter, and that's ultimately what chemistry is defined to be, the study of matter and how it undergoes transformations. And so for each of the new reactions, what I want you to keep in mind is as an ultimate goal is you want to be able to propose the products that you would see from reactions, or predict the products that would result from reactions, propose how you could use that reaction to generate some target molecule, like what starting materials would you need, and then propose a mechanism, that is some sort of description using curly arrows. Remember, in our acid-base reaction, we use curly arrows to show that the negative charge attracted to the positively charged H plus, and that's how the bond formed, to give maybe in some examples water. Okay, so these two things are principally important when trying to understand new reactions. Now, what I want to talk about for our first reaction, it's a good starting place. It's actually a fairly complicated reaction, but in terms of storytelling, it's a really nice one to get started with. That's the free halogenation of free radical halogenation of alkanes. Okay, so this is our first reaction that isn't some generic acid-base reaction and isn't balancing some combustion reaction. That is, this is the first reaction we look at where we want to be able to do the things I just mentioned: predict the products, propose how we can use the reaction, get to a target, and then propose a mechanism. Okay, now what this reaction does is this reaction converts alkanes into haloalkanes. And it uses free radicals. And we can actually specify where the radicals are. They're intermediates in the reaction. That is, they're not starting materials or products. They're those sort of ground states or wells or valleys between the various transition states in our energy diagram, but they're not all the way to the left. They're not all the way to the right. Okay, so what we'll notice is a critical new term for this module, and that is haloalkanes. We're actually only going to be talking about one reaction. Well, I don't know. We're not going to be talking about many reactions of alkanes. I should be careful. I've been wrong about stuff in the past as I try to predict these things. So haloalkanes are another functional group, and they're going to be a big part of this module. These are halogenated alkanes. Halogenated alkanes. So halogenated, that implies that a halogen atom has been attached to the alkane. Now, halogens are fluorine, chlorine, bromine, and iodine. Now, as it turns out, just based on its size and its electronegativity, it's sort of kind of like a just right or Goldilocks scenario here. Bromine is most often used. It's sort of the best for our purposes. It's not too reactive, but it's not too unreactive. And so what we'll see is a lot of the chemistry that we will describe as happening on haloalkanes will use bromine or brominated alkanes as the kind of go-to substrate to demonstrate the process. So we're using those elements to build new molecules, and these are halogenated alkanes. Let's go ahead and talk about some examples of halogenated alkanes. Okay, so I'm going to do the thing where I list a bunch of molecules, and you tell me if they're halogenated alkanes or haloalkanes. So I could ask the question, is this first molecule a haloalkane? Well, a halogenated alkane has an F, chlorine, bromine, iodine. Any of the other group seven elements really aren't that practical, so we'll just focus on those. And only CH, so it has the halogens and carbon and hydrogen as they are alkanes. So let me just get that. And we have sigma bonds. So halogenated implies fluorine, chlorine, bromine, iodine. Alkanes implies only carbon and hydrogen elements that are connected by sigma bonds. And so what we would say is this a haloalkane? Yes. The next one, yes, they only have carbon and hydrogen single bonds and then at least one halogen atom. The next one is no, it has double bonds. And the last one is yes, it has multiple halogen atoms, but that still qualifies it as a haloalkane. I don't want to get much more complicated than that. I don't want to show one that's got an OH and a halogen and expect you to be able to justify that, because it gets kind of diminishing. We hit diminishing returns quickly. Okay, anyway, that's just to give us a baseline. Oh, and then another one I should mention. So if you have just a CH3 attached to a halogen, whether that's a bromine, an iodine, chlorine, or fluorine, it still is considered a haloalkane. Just as methane was an alkane. Excuse me. Okay. So what we want to do is talk about the free radical halogenation of alkanes. And that again takes our alkane, and I'm going to leave some space because I'm going to add some things, converts into a haloalkane. Now the general reaction is shown here, but we can add some details that must always be present. You're going to take a haloalkane. To make a haloalkane, you need to have a halogen source. And I'm going to write that as X2. Now, X2 could be F2, Cl2, Br2, and I2. Now, for the most part, well, I won't even say it. Okay. What we need to do is recognize that we're going to have to balance this equation somehow. And to balance this equation, we need to have an HX on the opposite side of the chemical reaction. Now, where did the H come from? You could think of it as just the hydrogen that gets replaced with an X group. So, for example, if we treated methane with Br2, we could apply some reaction conditions where we replace the hydrogen atom with our bromine atom, and then we generate HBr as a side product. Now, maybe you want to see where the H comes from. It comes from one bromine atom and then one hydrogen atom, or excuse me, where the HBr comes from one hydrogen atom and one of the Br atoms that are attached together. So we have a situation like this, where one of those bromines is going to replace the hydrogen. Now, to do this reaction, we're going to use heat or light. So I'm going to write that over every arrow. So just to recall, the delta triangle is delta, which is the symbol for change or heat. Turns out that for a long time, I had thought that the delta implied change in energy, which could be brought upon by change in heat. But it turns out that the delta is a carryover of an old symbol for fire. So indeed, it does just literally demonstrate heat. So we have delta or H nu. So H nu, that's H, and that's nu. H nu is going to be Planck's constant, which is a physical number, times the frequency of light. And so light has a frequency and a wavelength. These are characteristic properties of it. If you take the frequency and multiply it by Planck's constant, this is just something you could do for any form of light. If it's red light or if it's yellow light, whatever. If you do that, you get the energy of light. Now, what we need to do is use light as a source of energy, just like we could use heat as a source of energy for our reaction to occur. So it's the energy of light that we care about. So instead of drawing a lightning bolt or a light bulb, we generally write H nu to say we need to energize this reaction, and we could use a source of light. Okay, where we to get the energy of that light, we write H times nu. So that's our symbol for light. I'm going to emphasize that down here. H nu is light energy. Okay, so we could turn on a light bulb, we could turn on a hot plate or add a Bunsen burner, and this reaction will proceed. Whether it's the generic reaction or the halogenation of methane, we could use we could do either reaction, and we could sort of light it up, I guess, with, yeah, anyway, maybe you get it at this point. So let's go ahead and start working with this reaction a little bit more. Just checking my notes to see what we have to be able to do. I think we have everything. So sorry for the stall there. I was just making sure I didn't miss anything in the general reaction. So what we want to do next time is start to build upon the skills we've talked about today to get to a point where we have, what am I trying to say? We have enough information to be able to predict products and predict approaches to use the reaction to make target molecules, and then work our way towards the mechanism. Okay, so that's what we're sort of building off of. But I guess that's it. We saw the first reaction.